Welcome. The title of my talk is Toward Compositional Models that Mitigate Bias and Responsible Model Deployment. My name is Vicente Ordonez Roman. I'm assistant professor in the Department of Computer Science at the University of Virginia, and I'm soon to join the Department of Computer Science at Rice University. I wanted to talk about fairness in computer vision, but before I go there, I would like to tell people in the audience here that might not be familiar with this topic, that this is a topic that has been tackled in the machine learning community for quite a long time. There is a lot of work going on in the machine learning community, but in the computer vision community, we're starting to see also some of that. My interest personally started back in 2016. We had been working on a data set of activity recognition. So you're given these images and the task is to recognize what are the people doing in the pictures. And so you can see here, the action would be the action of carrying something. However, we soon recognized that some of these images were very easy to recognize. And some of them were harder. So you can see here that people carrying backpacks happen very often in the data set. So we had the model doing very well on those images, but not so well when people were carrying objects that were a little bit more unusual, like somebody carrying a table on their backs. And perhaps this is unsurprising because we don't have a lot of images of people carrying tables in the data set, and this is not a very common situation. This is a demo we had for this system. We call it situation recognition because it did not only consist in recognizing the activity, but also the context and the actors and the objects that were interacting during the activity. So we call this situation recognition. So this is the top predicted output for this image. And so we often show this demo to people, and we run into this situation where, we had this kind of picture where apparently there's a boy washing his hands, and the top predicted situation says that there is a woman rinsing her hair on the sink in the context of a toilet. And the second prediction is that there is a man installing the faucet in the sink using his hand in some indoor environment. So these are the top two predictions. And so we thought, okay, the model got it wrong. Maybe this is, sometimes machine learning models just get outputs wrong. So what about this one? The second image, it shows a very similar situation, and the model makes the following prediction. So the top prediction is that there is a woman dusting the faucet with a towel in a room. The second prediction is that there is a woman vacuuming the floor using a vacuum in some room. So you can see woman seems to be co-occurring with things like cleaning things, and men seem to be co-occurring with things like installing the thing. So we thought, this is probably propagating some stereotypes, and to what extent is it doing that? Is it just the data set that is biased, and is the model just learning those biases? So these are questions that kept us working for a while, and initially we did the simplest thing, and this is something that a lot of people have been doing for various data sets, which is let's look at the bias in the data set, and is there any bias in the data set? So we look at the images of people cooking in this data set, and we indeed found that there were a lot more women cooking than men. And we looked at other categories. So in this data set, we found that cooking was not the more women biased category. There were others like washing or shopping or braiding that were even more skewed towards women. And there were other categories as well that were skewed toward men, like coaching, lecturing, or repairing. Datasets contain biases. So this is something we found. This is something a lot of people have found for various datasets. And if you keep digging, you might find that your dataset also has some form of bias. So the next question we had was, are these models replicating the biases? I mean, it would be almost unsurprising that they are. But what we found is that they're not only replicating the biases, but when we run this model on some test images, the model was predicting women as cooking a lot more than even its training data set. So there is this disparity, there is this amplification, we call it. So we call this bias amplification. And people often say that models are as good as the data they're trained on, and this is certainly true, but we often forget that the models could also easily be worse than the data they're trained on. and they could be worse in ways that we don't know. Like, what are the kind of mistakes the models are making? Cooking, again, which had a percentage of women of about 30%, went to 15% after in the predictions. But there were other categories for which this situation was worse, like washing was almost exclusively, the model was almost exclusively assigning women when the washing activity was predicted. And so this happened at test time, even though in the training data, there were some men washing things as well. So this is a paper that we actually got published at the EMNLP 2017. It won a Best Paper Award and introduced this idea of bias amplification. In this work, we also introduced a debiasing technique where we also try to keep the ratio of predicted men to women at test time as close as possible to the ratio in the training data. And we got a little bit better results. I mean, if we try to maintain the accuracy of the model when it comes to predicting the activities, we could get a model that was pretty close, and it had a ratio that was a little bit closer to the training data set. But certainly this is not a complete solution, although it does manage to mitigate some of that bias. This was a paper that was published the following year at Berkeley, Women Also Snowboard, Overcoming Bias in Captioning Models, by Kylie Burns, Lisa Ann Hendricks, Kate Sanko, Trevor Darrell, and Rohrbach. So here in this paper, they found that for the captioning task, there were also issues of bias. Sometimes the model would predict that there is a man or a woman, even though the model is not even looking at the area where the person is in the picture. So in this paper, they came up with a set of losses that were carefully designed so that if the model is really not paying attention to the person in the picture, then it should not predict something as specific as a man or a woman, but it should instead just use references such as person. The other very, very influential bias paper was published by Joy Bolamwini and Timothy Hebrew at FACT 2018. And this is called Gender Shades, where they found that commercially available facial analysis APIs that were actually being sold to other companies are biased with respect to women, and also especially women with dark skin. So what they found is that the gender prediction was not very accurate, especially for these demographics. And this has had a huge impact. Here's another paper. This is by Benjamin Wilson, Judy Hoffman, and Jamie Morgenstern. And this is predictive inequity in object detection. This is similar to the previous paper, but here they're looking not at face recognition, but pedestrian detection. And this is especially relevant if you care about issues of fairness as it comes to building things like self-driving cars. We also had a follow-up paper in 2019 at ICCV 2019, Balanced Datasets Are Not Enough, Estimating and Mitigating Gender Bias in Deep Image Representations. And here, what we did was that we found that there is bias amplification, even if we have a model that is not predicting the gender of the person in the picture. So the way we did this was we had a data set with object annotations only. So there is no person annotation or gender annotation. And so we try to train classifiers on top of the annotation. So we're trying to detect, like, what is the ability for a classifier to detect whether it's a man or a woman in a picture just by looking at the annotations for that picture, not looking at the actual picture. And we found that we could do these quite accurately, surprisingly. And moreover, when we train a model on such annotations, and then we try to predict the gender of the person, not from the ground truth annotations of the image, but from the predicted labels by the model, we could even detect the gender of the person. We could even like guess, I would say, the gender of the person at a much higher rate. So suggesting that perhaps the model is using some gender associations to create this new set of predictions, this new set of labels that are automatically assigned by the model. And so we found that the issue of bias amplification might be more pervasive than we had previously stated. And more recently, we also had a paper, and this is at ICSI 2020. So I guess most people here will not be familiar. This is International Conference on Software Engineering. So if you look at a machine learning model as a piece of software, then you will realize that like a piece of software has lines of code, in a neural network, which is a typical machine learning model used for computer vision tasks, we also have paths. And these paths can take different routes. And there are some unused paths that might be problematic at test time. And those might be like the ones that are like responsible for some of the bias. So we use some notion of neuron coverage, which is analogous to the test coverage that people do usually for software development. And we found a way of estimating whether there is some bias in the data set without necessarily having some extra data set that has an unbiased data set where we can actually probe the different types of biases that could exist in the data. And more recently, this is the work by Angelina Wang and Olga Rusakovsky at Princeton. And this is ICML 2021, Directional Bias Amplification, where they actually fix some of the shortcomings of our previous bias amplification metric. And turns out that sometimes we predict the category as men or women because of the activity, but sometimes it also could happen the other way around. We're predicting the activity as something because there was a person of certain gender in the picture or not. So this is called directional bias amplification. It fixes some of the other issues also in the metric. So you can read this paper, and it takes the issue of bias amplification to another level of analysis. So going back to this work, on top of like demonstrated that there is some amplification in annotations, we also found that even if you try to balance the training data so that you have 50-50 men and women, this doesn't quite eliminate the issue of bias amplification. On top of that, we also leverage this framework of adversarial removal of sensitive features. And this was something that was explored before by Brian Hu Zhang, Blake Lemoine, and Margaret Mitchell, mitigating unwanted biases with adversarial learning. So we apply this kind of technique, but to a deep convolutional neural network, where we found that if we apply these adversarial removal of sensitive features in some intermediate layer, that led to the best results. So we further refine this model so that we can make it interpretable. So as part of the deep convolutional neural network, we also have an autoencoder style neural network that we could use to see what is the adversarial gender loss trying to remove. And again, this is a model that was trained without object annotation, like without object location annotation. So the model is automatically learning that, you know, gender is correlated to facial features. So it tries to eliminate those. And also it tries to eliminate things that are correlated with skin color, and also with objects that might be, for instance, too stereotypically either male or female. In this case, like in this data set, it happens to be a pink umbrella. And it works even if you have multiple people, even though most of the images that we had in the data set had a single person. Again, we have a demo for these, so you can upload your pictures. It works on your phone. You can take a selfie and see what the model is trying to remove. It doesn't eliminate completely the bias, this adversarial mitigation method. So you can see here on the x-axis, we have bias amplification. On the y-axis, we have the recognition performance. So we want to have low bias amplification, but high recognition performance. So you can see here that we try several other baselines, like trying to just blur the faces of the people. Maybe that will remove the gender, while at the same time allowing us to recognize the objects. Turns out that the adversarial approaches that we tried were better than most of, like almost any of these baselines. And also in this line, you know, we have a paper here at the CVPR. This is a black box explanation of object detectors via saliency map. We propose a method for explaining the outputs of object detectors. And you would think that maybe object detectors just look at the object you're trying to detect. But actually, in some cases, it does give you insights that go a little bit beyond that. So you can see here, for instance, that in recognizing this laptop, the model is paying an outsized amount of attention on the logo of the laptop. We also have a bias experiment in this paper that I encourage you to look up. We try to introduce some biases at training time by adding like little blue dot markers around objects. So we added, for instance, here blue dots around the fire hydrants. And so at test time, if you add a blue dot, you can see that the model sometimes triggers for fire hydrant, even though there is no fire hydrant there. So you can see that the models can clearly pick biases like that. And these might be a very salient bias that we introduce, but there might be some other more subtle biases that are just in our data and we're not aware about. So this is a technique you could use if you wanted to make that kind of analysis. Okay, so we have made great progress in measuring and diagnosing, but what about solutions that go beyond mitigating bias? Can we make a model for which we don't need to design a bias mitigation technique, but the model itself is designed with bias mitigation in mind? Is such a thing possible? So here's one thing I wanted to propose, and this is the topic of compositionality. So some of these models are relying too much on just statistical correlations and not some other notion of how images are formed. So here I want to suggest that if you know some basic concepts, it shouldn't be difficult for you to reassemble them in novel and unexpected ways. For instance, here you have car, house, red, door, open, closed. If you understand these few set of concepts, you can probably picture what something like this might look like, a red house with a closed door. So it might look like that. And if I ask you to picture something like a red house with an open door, even though you might not have ever seen such an object, you can picture it if you know the individual concepts. And I will argue that a lot of the data sets, if you look at the houses in the data sets, most of the doors are closed, because that's what happens in real life. Most of the times doors are closed. The amount of times a door is open in your house is very brief compared to the number of times it's closed. However, you don't have a significantly harder time recognizing the house just because the door is open. Here's a particular problem we looked at in our group. This was the problem of image generation, and generative adversarial networks have been quite successful at generating pictures. So here is the picture generated for a flower given an input textual description. However, as things get a little bit more complex, like you want to generate chairs, you can see that the results become less satisfactory. And as you move to complex scenes like this one, a cat curled up on a skateboard in a living room, then it becomes even more difficult. We can look at the data set, and certainly there are not a lot of cats on a skateboard in the data set. Surprisingly, there is a large number of dogs. What if we could instead just create or synthesize a picture by borrowing objects from other images in the training data set, so that we can assemble a picture systematically piece by piece? And this is a run of our method on this input sentence. In the first time step, it produces the skateboard and it places it somewhere. Then it places the cat on top, and then it places some background, and we do some little in painting. And this was quite okay for the kind of quality that some of the GAN methods were generating for this type of scene. There are other works. I mean, more remarkably, recently OpenAI had this DALL-E method for generating scenes. And even though it's not exactly like generating things object by object, it's also not using just a GAN. I mean, it's certainly creating a vocabulary of patches that they can use a transformer to place in a scene. So the compositional aspect, I feel like it's still there. But the compositionality in other tasks is also exciting. So I'm especially interested in zero-shot learning. I really believe compositionality is an effective tool that we will be seeing to mitigate some of the inherent biases that are in current visual recognition models. In the meantime, I think one question we should ask is, what does responsible model deployment look like? And in order to answer some of these questions, I mean, a group of colleagues, Joy Bolamwini, Jamie Morgenstern and Eric Lern-Miller, we had this white paper called Facial Recognition Technologies in the Wild, a call for a federal office. So in this work, we argue that there are technical, societal, and legal challenges that come with deploying specifically face recognition technologies. But I believe some of the recommendations we make in this work could apply more broadly to AI or computer vision systems. One of the first challenges, in the societal challenge is the consent and disclosure challenge. Like facial recognition technologies can be applied without consent through public cameras. Facial recognition technologies might not disclose their capabilities and limitations. Privacy and surveillance, what are the expectations that the public has in public spaces, and are the systems that we're deploying breaching any of those? There are technical challenges that I think will be hard to overcome. Benchmarks, for instance, they do not cover all use cases. You might have a data set that works on daylight conditions, but it doesn't work in nighttime conditions or poor lighting conditions. Benchmarks cannot cover all type of deployment conditions. So I think one has to consider systems on a case-by-case basis. The poor performance on a benchmark can be taken as a warning sign, but a good performance on a benchmark does not necessarily imply that you have a green light for doing and deploying that system in whatever context. There are also legal challenges that, there are anti-discrimination laws, and there are currently proposed bans and also partial bans on facial recognition technologies. And here are a couple of them that I've highlighted. So here are the recommendations that we make in this work to mitigate these challenges. First is oversight. We're calling for creating an entity, in this case, a federal office, but we had a lot of debate about whether it should be federal or something else. And this was, again, in the context of the United States. For creating an entity that regulates deployments based on level of risk, transparency, also advocating for clear labeling. So the developers of the technologies should be responsible for convincing both the general public and also the experts in this regulatory entity that what is the purpose, the scope of the application, and that the technology that is going to be deployed is ready for that purpose and scope. We need expertise. That's the other thing. So we need experts weighing in, because there is no single benchmark that can account for all biases or use cases, but they can be used to take informed action on whether something looks like a responsible deployment or not. There are lots of other prominent examples other than facial recognition technologies. Twitter had this image cropping issue, and then Google has this image tagging issue, and then Amazon had this facial recognition issue, and Microsoft had this text generation chatbot issue. And again, Amazon had this issue with the recurring tool, and speech recognition has also shown instances of bias. And one recent example that I was actually asked to weigh in, and this is about technologies for monitoring older adults. And again, I was asked to look at some of the tools that are being advertised out there. And for me, it was very hard to assess, just based on the public information on the advertisements of these companies, whether even they're using cameras to make some of the assessments or other types of sensing technology. There were other issues like reported accuracies that were not very clear how they were obtained, in what kind of benchmark, under what kind of situation. It's not very clear that those metrics are communicated in the most effective way to the general public. So I think there are many use cases, although certainly I would say that this is one of the technologies that probably potentially has more benefits than harms in this case. And here are a couple of takeaways from my talk. Fairness and bias mitigation, as I mentioned, are well-known issues, and they are in some way mainstream research in machine learning already for quite some time. Biases exist in data, but they might also be amplified by choices in our models. So this is something that we have been looking at quite carefully, and not only just in our group, but in other groups. and data fixes are not enough. Compositionality could be a way to make models intentionally less biased. I mean, beyond just coming up with new bias mitigation techniques, how could we make our models a little bit less biased, at least from the start? And then finally, I hope you can ask me questions about model deployment. This is a complex issue that needs to be evaluated on a case-by-case basis. And finally, I will take questions. I want to thank my students, collaborators, and sponsors. Thanks very much.